In this session, we're going to make the situation a little bit more complicated. Now, we're going to send a wave at an angle from the surface normal of the boundary. And with this scattering configuration, you see the angle for the instant wave. Then we have to define the plane of instance, just like when we deal with the situation having the conducting boundary here, we also have to define the plane of instance so that we can then define the polarization direction of the wave. And in this scattering configuration, on the left-hand side, you have material 1 characterized by refracting index N1 or the intrinsic wave impedance eta 1. And on the right-hand side, we have the second material characterized by N2 eta 2. And in this example, I specify the electric field to be in the plane of instance. So this is a TM wave. So we're going to use TM wave as one example to show you the physics associated with this scattering configuration. And you can see that the instant magnetic field will be polarized perpendicular to this plane of instance. And remember that there's a relationship between the electric field and magnetic field. So if you could write down the expression for one of them, you can derive the other. For this scattering configuration, the easiest expression for the field will be the magnetic field, because your magnetic field only has component along y direction. But for the electric field, on this plane of instance, you have two components, one along z direction and the other along x direction. So first write down the magnetic field for this instant wave, and it's polarized along y direction. And there's amplitude, which is the instant electric field divided by the intrinsic wave impedance in the first material. And the propagation has an angle with respect to the surface normal direction, and I denote it as theta I here. And the reflected wave will have an angle theta r from this surface normal direction. For the transmitted wave, the angle from this surface normal direction is theta t. Given these angle definitions, then we can write down the phase term for this complex exponential. And you can see that the wave propagates along the plus z direction and also plus x direction. Therefore, you have minus j beta 1 multiplying with this x sine theta I plus z cosine theta I. And once you have this expression, you use this formula to write down the instant electric field. So you just plug the expression into this formula, and you get this result right away. And if you think this is a little bit complicated, you can go back to the last lecture and look into the field expression associated with the conducting boundary. Then immediately you can realize this. Except that now in the first material, we have eta 1 in this expression and also beta 1 in this expression. Just try to include the material properties into the field expression. So you can do the same thing for the reflective field. Write down the magnetic field first, because the direction of the magnetic field is very simple. You only have component along y direction. So you write down this expression. But you can do a little bit of checking on this expression, because you know that this reflective field will be propagating in the minus z direction and plus x direction. So you can check the sign here. You have the plus x and minus z in this expression, and in front of this j is the minus sign. And again, use the formula we have on the last page to write down this electric field expression. Now, just follow the same process. You can also write down the field component for the transmitted wave. but this time you need to be careful that this wave is in the second material. So the propagation constant has to be labeled with 2. At the same time, the intrinsic wave impedance has to be labeled with 2 as well. Okay, and again, those components in the second material will be propagating around z plus z direction and plus x direction. So you have a minus sign here, and you have plus sign here and plus sign here. Once you write down all the expressions, now is the time to apply boundary conditions to figure out unknown parameters. So the boundary conditions associated with the two-direction materials. At the boundary, you don't have charges, you don't have currents. So the tangential component of the electric field and magnetic field are continuous. So you try to extract the tangential components from the last 3 sets of expressions, which is the component along x direction, because the component along z direction is perpendicular to the boundary, and you don't want to use them for these boundary conditions. So once you extract the x component and also the y component of the field, then you can write down 2 expressions, because the x component and also y components are the tangential components with reference to the interface. So if you look at these 2 expressions, it appears to be a little bit complicated, because the only thing you know about is EI0, because this is the amplitude you send into the problem, you send into the interface. And you do not know the angle theta r and theta t, but you know the angle theta I, because in your experiment you specified theta I to be the instant angle. And you do not know the refraction amplitude, and you do not know the transmitted amplitude. It turns out that you have more than 2 unknowns in these 2 expressions. But the good thing is that we discussed this about the instant of the wave on the conducting boundary, and we know that the wave will impose a boundary condition, which is that the wavefront at the boundary have to be continuous. Therefore, all the complex exponential have to be the same. So if you just extract the complex exponential and set the phase to be the same, then you have this requirement at the boundary. So you pull out this complex exponential and right here, and also pull out this complex exponential and right here, and then you have the transmitted complex exponential and set it here. Then this tells you that at the boundary, the wavefront have to be continuous. And this is the very strong point that for all the waves, they have to follow this boundary condition. And or you can just write down beta 1x equal to beta 2x. Beta 1 is the propagation constant along x direction in the first material, and beta 2x is the propagation constant along x direction in the second material. So with this requirement, you can write down immediately that this has to be equal to this, and this has to be equal to this. So if I just spell it out, it says that the beta 1 sine theta I equal to beta 1 sine theta r. So with this condition, you get theta I equal to theta r, which is the condition we call Snell's law of refraction. And we already have this when we talk about a conducting boundary. And the second condition is this: the beta 1 sine theta r has to be equal to beta 2 sine theta t. And if you just use beta equal to 2 pi over vacuum wavelength multiplying with the refractive index, then immediately you end up having this expression: n1 sine theta I equal to n2 sine theta t. So this expression tells you if you have a refractive index n1 here, refractive index n2 here, and if you know the instant angle, then you can get the refractive angle theta t from this expression. And we call this Snell's law of refraction. Now, let's take a little bit close look into this, the Snell's law of refraction. N1 sine theta t, N1 sine theta I equal to N2 sine theta t. And suppose that you have a larger refractive index in the first material, and then you have a smaller refractive index in the second material. And for this scattering configuration, we call it internal refraction, with higher refractive index in the first material and lower refractive index in the second material. Given this condition, you can see that the refractive angle theta t will be larger than the incident angle theta I. So if I continue to increase the incident angle of this instant wave, say if I continue to increase to this angle, well, eventually this theta t will reach the point at 90 degrees. So at this point, this angle we call it critical angle, because now the wave cannot penetrate into the second material. And this critical angle is equal to n2 over n1, because you can set theta t equal to 90 degrees, and you get sine 90 degrees equal to 1, and you move this n1 to the right hand side. So you get this critical angle to be the arc sine of n2 over n1. And if you continue to increase the instant angle to be larger than this critical angle, turn out that the wave cannot go into this material. You get total internal refraction. And this is the phenomenon that we often use when we do the optical fiber communication. And I'm going to talk about it on this page. So think about that you have a piece of optical fiber and you have two materials, one in the core and one in the cladding area. So this is the cross-sectional view of the optical fiber. You have a core with the refractive index of n1, and you have a cladding material with a refractive index of n2. And the functioning principle of an optical fiber is that you send an optical signal into this optical fiber and allow this wave to bounce back and forth inside the material boundary. And if the instant angle, the theta 1, is larger than the critical angle, then all the energy of the optical wave can be confined inside this piece of optical fiber. So the condition is that the sine 1, the theta 1, sine 1 has to be larger than the sine of the critical angle. And from the last page, the sine theta critical angle is given by n2 over n1. Now the question is, what could be the maximum instant angle, the coupling angle theta, so that the wave can be confined inside this optical fiber? Because you don't want to send an optical signal that cannot be guided inside this optical fiber. So now let's try to figure out what could be the maximum angle here so that this theta 1 can be always larger than the critical angle. So let's use the Snell's law at this boundary. Snell's law tells you that if I have a refractive index of n here, quite often this n is air equal to 1. So you have n sine theta for the instant angle theta here equal to n1 sine of this angle. And this angle is equal to 90 degrees minus this theta 1. So I put 90 degrees minus theta 1 here, which will give you n1 cosine theta 1. Now, the condition is that the sine theta 1 has to be larger than sine theta critical angle for the wave to be guided inside. So if you change this sine to cosine, then you have to flip the direction of the large or equal valued sign. You change it to equal or less value sign right here. So cosine theta 1 has to be less or equal to cosine theta c. Then you copy down this expression to this, and then put the condition into this expression. So you have this expression less or equal to n1 cosine theta c. But you know sine theta c is equal to n2 over n1, so you can continue to write this cosine theta c to be this value. So on the right hand side, you only have an expression of the materials as a function of n1 and n2. On the left hand side, you have angle theta corresponding to the coupling angle here. So you know that the angle theta has a maximum value equal to this one. So you write down n sine theta maxima corresponding to the maximum angle here for the wave to be guided inside the optical fiber, and then just copy down the result on the right hand side to be this. And this tells you how you want to couple the wave, the optical wave, into a piece of optical fiber. You cannot send a wave with an angle larger than this value. Otherwise, your wave cannot be guided inside this optical fiber. And this is called the numerical aperture of this optical system. If we consider this optical fiber as an optical system. So this term is commonly seen when we talk about an optical system. All the wave has to be propagating into the system confined by some maximum angle. It's quite interesting that we see a condition where you don't have wave penetrate into the second material. So if you have a material N1 larger than N2, and then your instant angle is larger than the critical angle, the field cannot penetrate into the second material. And this is given by the Snell's law of refraction. But now we want to see this result from the theory of electromagnetics. And to know the propagation in the second material, we have to know the propagation constant beta 2z from this diagram, because beta 2z is the propagation constant along the z direction. And so what happened to this beta 2z when theta I is larger than the critical angle? First, let's write down the field expression, the complex exponential plot of the field expression in the second material. And it is written as exponential minus j beta x minus j beta 2zz. And this beta x is the beta, the propagation constant along x direction, which is the projection of beta 2 onto this boundary, or beta 1 onto this boundary. And we said that this beta x projected from beta 2 and beta 1 have to be the same, because at the boundary, the wavefront have to be continuous. And that's why that from this relationship, we have the Snell's law of refraction. But this expression will allow you to calculate the beta 2z by substituting this value into this expression. And this expression, beta 2 squared equal to beta x squared plus beta 2z squared, is given by Helmholtz equation. So now let's just put this result into this expression and try to understand what beta 2z is. So after some algebra, of course, you have to use the Snell's law of refraction and put it into this expression. But I don't want to go through all the details, because this could confuse you. You can just do the derivation by yourself. And the important conclusion is that once we finish this calculation, we found that when instant angle is larger than the critical angle, the propagation constant along z direction in the second material become a pure imaginary. So this means that the wave cannot penetrate into the second material, and the field in the second material is going to have exponential decay from the boundary. Think about that. You send the wave in this direction and then bounce back in this direction, but the field in the second material is not propagating, and the field component or field amplitude will drop from this boundary exponentially. So this is what happened. A wave under this scattering configuration, the instant angle is larger than the critical angle, then the wave will have the attenuating amplitude in the second material. And we call this wave as evanescent wave because the field in the second material basically just die away along the z direction. Now, I want to summarize this section a little bit. 所以呢，如果说我们有个波 朝着一个这个接电物质的界面打过去，然后有个角度在那个地方的话，那这时候呢，我们可以得到两个很重要的条件。这两个很重要的条件呢，来自于波在边界上头的这个波前的连续。那第一个条件叫做 Snell's law of refraction， 也就是入射波的角度跟反射波的角度会一样。那另外一个条件呢是 Snell's law of refraction， 也就是这个折射率的这个公式。那告诉你说，如果说我这个有一个入射角度，然后第一个物质是 n1 的这个折射率，然后它会等于 n2 第二个物质的折射率乘上折射的这个角度，这个折射角度的 sin， 那这个叫做 Snell's law of refraction。那有趣的是，当这个第一个物质的折射率比第二个物质大的时候呢，我们把它叫做 internal refraction。在这种状况之下，存在一个critical angle theta c， 在这个 theta c 的时候呢，在第二个物质里头的这个 refraction angle 呢会是90度，也就是这个波开始进不了第二个物质。那这个 sin theta c 呢会等于 n2 over n1。那这个条件会开始就是产生内部全反射，也就是说，当你的入射角度大于西塔 c 的时候，你会有内部全反射。那这个也是一个光纤传输光的讯号的一个基本的原理。那当这个入射角度大于这个 critical angle 的时候呢，这个波的场在第二个物质里头，它会有一个指数消减的一个现象。那这个波在第二个物质里头是不传播的，我们把它叫做消散波 （evanescent wave）。那这个是第3节里头的一些重点。谢谢。